Questions from chapter 24?
Question 75.
I don't know, actually. I just did a very fair scan of the questions I put down before. Conducting rod carrying a total charge of, yeah, I just realized earlier today that if I answered yes or no to whether it's on the quiz or not, then very quickly you would narrow down to the 2 questions. So I'm going to try not to make a habit of that also.
We'll just ask all the questions.
Pardon?
We'll just ask about all the questions.
Yeah, that doesn't seem like the best use of time. But, I have had classes that do that.
Yeah.
A conducting rod carrying a total charge of 9 microcoulombs is bent into a semicircle, and there's a picture. It's convenient. With its radius, the center of curvature at the origin, charge density is given by that equation. Magnitude of the electric field on a 1 microcoulomb charge placed at the origin. All right, so the charge they put at the origin is irrelevant.
Should be 0.
Pardon?
Should it be 0?
It will not be 0. It will be more complicated than that. And matter of fact, we can't have the symmetry, or can we?
Yeah, the y component cancels out. So you won't get 0.
Yeah, because it's based upon, yeah. So the charge density is based upon the sine of theta. I always hate writing on a fresh, clean board. At the same time, I appreciate writing on a fresh, clean board. So we know that the linear density is equal to some constant times the sine of theta, and they define theta to be this angle right here. So there's going to be no contribution on the ends here, and it gets stronger and stronger as we get closer to the middle. Because sine theta is symmetric over that angle range there, we do have the argument that all the horizontal components will cancel out, and we're only left with the vertical component in the end. So what other information do they give? Without fogging up my glasses. So this is a total charge of 9 microcoulombs. Radius is 33 centimeters. They give it another significant figure, but I'm not caring about those. All right. And so what's the electric field there, I believe? Just go back to the basics. We have a charge distribution, so I can't use the point charger formula in a straight plug and chug. I have to create a differential. May as well make it right there. So I have some infinitesimally small bit of charge right there. And so I know that my electric field is going to end up being the integral of, I guess, bring the k out, dq over r squared. And then we have the directional piece that my electric field is pointing in that direction right there with that angle theta, but we only care about the vertical component. Sine theta, and let's go ahead and go with the typical brainwashing j hat. Now we can check to see if we're doing it the right way by bringing in the I hat component also, and then we could work that out. And if it doesn't end up being 0, we've done something wrong. Well, again, we only care about the component that ultimately is going to be vertical. dq I know that the charge, that the linear charge density is equal to dq over dl. So dl would be basically how far it is along that arc length. And so dl, since it is part of an arc length, would be equal to rd theta. Because if you imagine we have that tiny little bit of wedge right there, where this is some infinitesimal change in theta, so this is d theta right here. That distance there is r, and that's just our arc length, which I've labeled as dl in this particular case. And so let's put the pieces together. So therefore dq is equal to lambda dl. Lambda, I know, is equal to some constant times the sine of theta. dl is equal to r d theta. And my radius is constant, so let's just, I can chug a little bit. So I got k on the outside, got j hat on the outside, I got r squared on the outside. Bringing this in, lambda sub naught is constant, r is constant, and I'm left with sine theta d theta squaring the sine. Did I leave anything out there? Let's see, so I've got the k, j hat, and the r squared, the lambda sub naught, the r, and then I'm left with the sine thetas and the d theta. Okay, there we go. And theta is going to go from 0 to pi. So now it's a matter of what's the integral of sine squared d theta. Sine squared theta d theta.
Wait, why do we square the sine theta?
Why is it squared?
Yeah.
We got two sine theta. One of the sine thetas comes from here, from the charge distribution. The other sine theta comes from the components. That the electric field from this differential is in that direction. This angle here is theta. So technically the electric field has some magnitude times the horizontal component, which would be cosine theta I hat, plus sine theta j hat. Since I know the I hat components, ultimately that's going to just cancel out. We're left with the sine theta there. So this sine theta comes from the component, from the vertical component, and the second sine theta comes from the charge distribution. Other questions up to here? Any silly errors that I've made?
I think my confusion is, like, on the answer sheet, it says that it's the y that cancels and the x adds up. That's why I was really confused.
Did I misread?
I think it's because you're doing electric field and not force.
But still.
Oh, I misread. What's the magnitude of the electric force? So that 1 microcoulomb charge does matter. But the only thing that changes, I mean, solving for the electric field's fine, and then we'll just multiply times that one charge there. But you said that the solution canceled out the other?
Yeah, it says the force in the y direction is equal to 0.
There you go, Doc. Oh, yeah.
Actually, I have it here. Oh. Yeah, I've got a big old mark right through my solution here. Oh. Yeah. Yeah, I put a slash through it and says does not match problem. I guess I did not make a note on the.
Oh.
would explain some confusion there. I am feeling comfortable with this. Apparently they had, because they defined X and Y under the traditional means, their semicircle was this way, or that way, instead of that way, in the way they solved it. Well, that's an easier integral to do. Ah, we're here now. So what is the integral of sine squared theta? Or how would you go about it?
Integration by parts.
Okay, what's another approach?
You give it to us.
You said double angle?
Yeah.
And you said I give it to you?
Yeah.
I will look it up.
Okay.
So it's along the same lines. It's physics. So I'd go to my table of integrals and look up the integral of sine squared theta. I don't know it off the top of my head. Is integration by parts because you'd have sine and sine.
Yeah, it'll cancel out eventually. I've done that integral with
Okay.
integration by parts.
Oh, so what's the answer?
I know it's like 2 sin theta, something like that. I don't remember. I know I can work it out. Tabular is generally easier if you do tabular and then cross or cross.
All right, but Precious, I think, is looking it up right now, or you get sidetracked on something else.
Yeah, I'm trying to look it up.
You know, eventually you get old, you stop doing the calculus the hard way and start just become independent on someone else having done it for you.
I think it's half times the, hang on. It says to use a half angle formula.
I think it's 1/2.
I guess they have assigned to the n theta?
Yes.
That's a sine squared?
There's a sine 2 theta in there, minus.
All right, so we have the angle formula, which I think might be a little bit faster. I know that
1/2 of x minus 1/4 sine of 2x plus c.
so 1/2 theta minus 1/4.
No,
Sine 2x.
Sine 2
Sine
theta.
2
Sine 2
theta.
theta.
Yeah.
All right, from 0 to pi. Now the question is, could we have done it faster going from scratch or by having someone else look it up? Stick pi in here, we get pi over 2. That'll be 0 with pi in it. Stick 0 in and we get that's 0 and that's 0, so pi over 2. So we end up with k over r, that cancels out there. Lambdas of naught pi over 2 j hat. Yeah, because that cancels out both times there, I think. It's not really an acceptable form of final answer because there really should only be one fraction bar per answer. If you have a second fraction bar, it better be, you can have units with one fraction bar also. That's a separate thing. So, k. I probably should write that down. Oh, and there are actually numbers you can plug in at that point, but I think we're past the point of where the really confusion was.
So the question was asking for lambda sub naught. So lambda?
The question was asking for the force. They said electric force, and so being a sloppy reader, I read that as electric field. Find the electric force on a charge that's sitting right here. That's the electric field at this, the net electric field at this point. So then you would just multiply times the charge here to get the force itself. They gave us R, K we know, pi and 2 are just numbers, and then the lambda sub naught. We would find. Because I know the total charge is 9 microcoulombs. So we can find the lambda sub naught. Because if I have some charge here, d lambda. Is that the approach I want? Wait a second. Oh. That's dq right there. So if we integrate both sides, we get the total charge is equal to lambda sub naught r integral of sine theta d theta from 0 to pi. We know q, we know r, we can do that one. And so we can find out lambda sub naught from that. And there's probably a shortcut in there that I'm not seeing, but that in essence is how you do it. Presumably they did that. Yeah.
Did you say we were given Q? Or
We were given that the charge along this semicircle was 9 microcoulombs.
So then the Q there would be what would be 9 times 10 to the negative 9?
Micro 10 to the negative 6.
Oh.
Did you want me to put numbers in this?
Yes, please.
Okay. So my charge here is given as 9 times 10 to the negative 6 is equal to my lambda sub naught, which I'm trying to find, times r, which is 0.33 meters, times this integral here, well, the integral of sine, negative cosine, from 0 to pi. Stick in pi, you get, that'd be negative 1 or positive 1 with that take that into account. So we get, let's bring the negative out front, negative lambda sub naught times 0.33 times negative 1 minus 1. So I have 9 times 10 to the negative 6 is equal to, well, that's negative 2 times that negative gives you 2 times that, so I have 0.66 lambda sub naught. So lambda sub naught would be whatever that is.
I think it ended up being 13.64.
Times 10 to the negative 6
Yeah.
coulombs. And so the electric field at that point would be 9 times 10 to the 9th times pi times 13.64 times 10 to the negative 6th divided by 2 times the radius, 0.33, J hat. That's going to be a big number. Oh, that'd be coulombs per meter. What does this end up being?
584,336.23.
584,000.
336.23.
It is the electric field, J hat, newtons per coulomb. And so since the force is equal to the charge times the electric field, so the force on a charge in an electric field is equal to the charge times that electric field at that point. And so that would be 9, not coulombs, 1 microcoulomb, 1 times 10 to the negative 6, times 5.843 times 10 to the 5th. So 0.58433623 newtons, J hat. Ooh. I figure that's what's going on in your head. I feel like there's a mistake in there somewhere, but I think the spirit of the problem has been done. All right, other questions?
Number 53.
Uniform electric field. Permeate the region of space in which a small negatively charged sphere of mass, yada, 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 suspended from a light cord. The sphere is found to be in equilibrium when the string makes an angle of 23 degrees. Charge on the sphere, and so on. All right. That is enough. So problem 53. So that I know that there is a force acting at some angle in this direction. Yep. So there has to be a force in that direction. My electric field is traveling in this direction right here. Therefore, what do we know about the charge on that sphere?
It's negative.
Yep. We have a weight acting down of mg. And we have a tension acting this way. Or writing this out a little bit better. We have some electric force acting in that direction. We have tension acting that way. And then we have the weight acting down. I know that this angle right here is theta, which is 23 degrees. And that angle right there we can figure out based upon the electric field. They tell us the electric field is 2.65 I. .35 J hat. Times 10 to the 5th newtons per coulomb. From this, I know my electric field, 2.65 this direction, 5.35 in that direction. Called angle phi right there. Because that angle right there, the force has to be the opposite direction to it, so that angle phi right there would be this angle phi right here. Despite the way I've drawn it, that is a right angle there. So I can find phi. I know the tangent of phi is 5.35 divided by 2.65. What's it, 70-something degrees? What is it?
63.6.
And so, it's an equilibrium. I need to break it up into components. Probably the simplest, considering the angles that we're given, is breaking it up into I and j hat components, the traditional horizontal vertical. Tension, therefore, is mg acting down. We have the tension times the cosine times the sine of 23.0 degrees to the right. Tension times the cosine of 23.0 degrees. And let me just double check. The angle they gave us is indeed against the vertical. And then the electric force times the cosine of 63.6 degrees and Fe sine of 63.6 degrees. Classic force diagram, acceleration, coordinate system, or coordinate axes, decomposition, equations of motion. What are the two equations of motion? Has it really been that long? All right, we got I hat, j hat. You were saying?
J Fe sine 63.6 plus Ft cosine 23 degrees minus mg is equal to 0.
I hope so. It's an equilibrium. My I hat equation?
Ft sine 23 minus Fe cosine 63.6 equals 0.
And now it's a math problem. We can solve for Fe. Well, there's several ways of doing it, but they tell us the mass, don't they? 1.3 grams. So my mass, 0.0013 kilograms. I assume it takes place on Earth, in some generic spot on Earth. If we solve for Ft in the first equation, plug it into here, then we can solve for Fe. Fortunately, it's not a complicated math problem. And once we have Fe, I know that's going to be equal to the charge, which we're trying to find, times the electric field. And, well, actually, we have the vector piece would go like that, but we know that the force and the electric field are in opposite directions already. So that's where we want to stick the minus sign. Fe is the magnitude this E right here is the magnitude, so I'm gonna put in the direction like that. I know they'll be opposite. F, E, and E are opposite signs. And solve for Q, because they give us that information. We find that this from here, solve for Q. We could have also just put this in earlier. And I suspect we could have probably taken some shortcuts in there too, but why? That just makes it pass that much faster. I think Austin, you asked for this one. You good so far?
Yeah.
Did you need me to see it? Did you need to see it through the end?
Not really. The main thing that I'm confused about is like, I think on the solutions that you had online, it didn't find the angle for the force from the electric field there. It just plugged in the I hat and J hat magnitudes of it.
Yeah. See, that was 53. Oh, yeah. So for this right here, they did the charge times the electric field in the, they call it X direction. Yeah. And here. But I'm not sure that it mattered which approach that you took.
Probably not. It's just what kind of confused me, because I saw it done that way, and then with the angles here, I was like, that looks different. Okay.
I broke it down to the basics, you know, sort of the mechanics approach to it, just
Yeah.
because the minus signs are a bane of my existence for 252, and I didn't want to mess the minus sign up.
Right.
So that's why I solved for the magnitude, as opposed to breaking up the components at that point.
Mhm.
And that's just personal preference.
Gotcha.